This video is looking at simple covalent structures, sometimes known as simple molecular structures. I want to show you guys how to spot covalent molecules first of all. The best way to spot a molecule is what you're looking out for is more than one non-metal atom that has been covalently bonded together. And the key word there, I think, is non-metal. You're looking for non-metal atoms interacting with each other. And we're not talking about giant structures here. We're talking about small, discrete molecules with only a small number of atoms involved. So I've got some examples here. We've got chlorine, we've got ammonia, which is NH3, we've got water, H2O, we've got methane, CH4. These are all examples of covalent molecules. What does covalent mean? A covalent bond is a shared pair of electrons between two non-metal atoms. So you can see between these two chlorine atoms in this chlorine molecule, we have one covalent bond, which is strong here, shown by the dot and cross, the shared electrons in the sharing area here. But what actually is a covalent bond? How does it work? All chemical bonds are strong electrostatic force of attraction between particles. In the case of covalent bonding, we're talking about strong electrostatic force of attraction between the positive nuclei, the two positive nuclei of the two atoms, and the shared pair of negative electrons found between them. So these two positive nuclei are being pulled strongly towards, attracted towards these shared electrons in the center here, creating the attraction, creating the covalent bond, which holds the whole molecule together. I now want to talk about the properties of simple covalent structures, and they're very different to the properties of giant structures. The first thing I want to emphasize is they have low melting and boiling points. And I want to think about this with a thought experiment. When you boil a kettle in your house, you are not breaking down water molecules into hydrogen and oxygen atoms. That's because those water molecules contain those strong covalent bonds as shown here. Those strong covalent bonds require a large amount of heat energy to overcome, way beyond the range of temperature which a kettle can produce. So you are not breaking down water molecules and the covalent bonds within water molecules when you melt or boil water. Instead, what's happening is that between water molecules in the liquid state, there are only weak intermolecular forces. Think of the term international flight between different continents. Inter means between. So between these molecules of water, there are only weak intermolecular forces, weak attractions, way below the strength of chemical bonding in terms of relative sense. So these are much weaker than the internal covalent bonds inside these water molecules. These dashed lines are my weak intermolecular forces. My solid lines are the strong covalent bonds. These covalent bonds don't break. When you sufficiently heat water to cause it to boil, you're breaking and overcoming these weak intermolecular forces only. That require a lot less heat to overcome compared to the covalent bonds. Hence why molecular structures like water have relatively low melting and boiling points, because all you're overcoming to move those molecules apart and change their state is the weak intermolecular forces between the molecules, not the covalent bonds inside the molecules. There are differences, of course, between different molecules, and it turns out that larger molecules have higher melting and boiling points than smaller molecules. And a good example of this would be the halogens to consider. So I've got chlorine, bromine, and iodine molecules shown here in a pretty simplified manner. But what I've also written next door is their melting points. And you can see that as you go down the group and the molecules get larger and larger, and the atoms inside the molecules get larger and larger, the melting points seem to go up quite dramatically. So it appears to be the case that larger molecules are forming stronger intermolecular forces compared to smaller molecules. This leads to the larger molecules requiring larger amounts of heat energy to overcome those increased strength intermolecular forces to melt or boil them. I'm not saying that these intermolecular forces are suddenly not weak. They are still weak compared to chemical bonding. But the larger the molecule gets, the greater the strength of the intermolecular forces involved, and therefore the greater amount of heat will be required to overcome those intermolecular forces to cause those molecules to melt or boil upon heating. Those molecular structures that melt or boil upon heating. The final idea is about conductivity, electrical conductivity. So, simple molecular substances do not conduct an electrical current. Think about what you need for electrical current to flow through a wire, in a metal, for example, or through other substances and structures you've covered before. For an electrical current to flow, you need charged particles to be moving. Now, molecular substances which have no overall charge just lack that capacity. So unlike ionic compounds, unlike ions, neutral molecules have no overall charge. So when you melt a molecular structure and make those molecules free moving, it does not conduct a current because there is no overall charge. There are no charged particles flowing or moving, and therefore they do not conduct electrical current. So first thing is there are no ions. Neutral molecules have no overall charge. When they flow, they do not conduct electrical current. Secondly, simple molecular structures do not have delocalized electrons that can flow between the molecules. And therefore, again, they cannot conduct a current. Unlike in metals, which contain delocalized electrons which can flow throughout the structure and conduct an electrical current, simple molecular substances do not have delocalized electrons that can flow between the molecules and therefore cannot conduct an electrical current. They are not conductors. That summarizes the key physical properties of simple molecular structures.